Nearly 300 million years ago, the Earth carried a landscape that would feel almost unrecognizable to us today. The continents were arranged differently, the forests followed unfamiliar patterns, and the air itself held a quality that modern life has long forgotten. Across the warm equatorial regions of the planet, immense wetlands stretched as far as the eye could see. These were not forests in the modern sense. The plants rising from the shallow water looked strange to human eyes, tall trunks covered in patterned bark, crowned with clusters of leaves that spread high above the swamp below. Dark pools of water reflected a hazy orange sky. Thick mist hovered just above the surface, drifting slowly between the towering vegetation. The atmosphere felt heavy and humid, dense with moisture and the quiet scent of decaying plant life that had been gathering in these wetlands for countless generations. Everything in this ancient world moved slowly. Water slid gently through narrow channels, carved between the roots of enormous plants. Leaves shifted softly in the warm air. Beneath the surface of the swamps, unseen creatures stirred the mud where layers of organic material were quietly building the foundations of future rock. For long moments, the scene appears peaceful, almost silent, then something moves above the forest canopy. A shadow glides across the surface of the water, stretching and bending across the ripples below. At first glance, the shape seems familiar. It might be mistaken for a bird drifting through the warm air, or perhaps a bat crossing the swamp at dusk. Yet neither birds nor bats exist in this ancient world. As the shape drifts closer, the truth slowly becomes visible. Two long wings, spread wide against the glowing sky. Their surfaces catch faint glimmers of light as they move with slow, steady rhythm. Beneath them hangs a narrow body built perfectly for flight. The creature passes overhead, silent and controlled. It is not a bird, it is something far older, a giant dragonfly, like insect gliding through the carboniferous sky. Its wings stretch nearly 70 centimeters across, wider than the wings of many modern birds. The delicate veins inside those wings form intricate patterns, strong enough to support its weight, while remaining light enough to ride the warm currents drifting above the swamp. Below, smaller insects scatter among the dense vegetation. Amphibian shapes slip through shallow water. The giant flyer circles patiently, scanning the wetlands beneath it. For the creatures of this world, nothing about this scene is unusual. In the modern age, insects are small, fleeting presences. They flicker past our attention before disappearing into grass or trees. Most people hardly notice them at all. But in this ancient landscape, insects held a very different place in the natural order. Some dragonfly relatives reached sizes that rivaled modern birds. Massive millipede-like arthropods crawled slowly through the thick vegetation, their armored bodies stretching longer than a human arm. Scorpion-like predators moved carefully through the damp forest floor. The air and the land both belonged to arthropods. For millions of years, these creatures flourished in ecosystems that operated under conditions unlike anything on Earth today. The atmosphere held far more oxygen than modern air. The wetlands stretched endlessly across warm continents. The environment allowed insects to do something that now seems almost impossible. They grew. Generation after generation, evolution pushed their bodies to larger scales, shaping wings capable of gliding through heavy air and armored shells that protected them in dense swamp forests. To the life forms living during that distant age, none of this would have appeared remarkable. Giant insects were simply part of the everyday world, as ordinary as birds or butterflies appear to us now. Only when we look back across hundreds of millions of years does the scene begin to feel strange. Because if insects once ruled the skies at such enormous sizes, the planet that allowed them to exist must have been profoundly different from the one we know today, and that realization leaves a quiet mystery waiting in the background. How do we know this forgotten world was ever real? The quiet swamp world fades, and the story moves forward across an immense stretch of time. Millions of years pass in silence. Forests rise and vanish. Oceans expand and retreat. Continents drift slowly across the surface of the planet. Eventually, the wetlands that once sheltered giant insects disappear beneath layers of sediment buried deep within the earth. What remains of that world is hidden inside stone. Today, in places scattered across the globe, Scientists kneel over ancient rock layers that were once soft mud at the bottom of prehistoric swamps. With small brushes and careful hands, they remove grains of dust that have rested undisturbed for hundreds of millions of years. At first, the rock appears ordinary. But as the surface clears, faint patterns begin to emerge. Thin lines branch outward across the stone in delicate symmetry. The lines form an unmistakable shape, long, narrow structures spreading outward like fragile glass. These are wings, not the wings of any insect that lives today, but the fossilized remains of something far larger. One of the most remarkable examples belongs to a creature known as Meganeura, an ancient relative of modern dragonflies, preserved in stone. Its wings stretch nearly 70 centimeters from tip to tip. Even after hundreds of millions of years, the structure of those wings remains visible. Tiny veins spread across their surface in intricate networks, each one frozen in time. When this creature once flew through Carboniferous skies, its wings would have rivaled the size of many birds. And yet it was not alone. In museum collections and fossil beds around the world, other discoveries reveal fragments of the same forgotten ecosystem. Slabs of rock preserve the outlines of massive arthropods that once crawled across ancient forests. One of the most striking is a creature called Arthropleura. At first glance, its fossils resemble the tracks of a long segmented machine moving across the ground. But these impressions tell the story of a living animal, an enormous millipede-like arthropod that may have reached lengths of 2 meters. Its body was composed of dozens of armored segments arranged in long rows. When it moved through prehistoric forests, it would have appeared like a slow-moving train of protective plates gliding across the forest floor. Other fossils reveal ancient scorpion, relatives that inhabited the wetlands of the time. Some species were far larger than modern scorpions. Their curved tails and armored claws adapted to life in dense vegetation and shallow water. One by one, these discoveries reveal pieces of a world that once thrived under very different conditions. The fossils are not isolated curiosities. They are fragments of entire ecosystems. In that distant age, arthropods filled roles that today belong to very different animals. Giant dragonflies ruled the air as aerial predators. Massive crawling arthropods recycled decaying vegetation across swamp forests. Scorpion-like hunters moved through shadows beneath towering plants. The world was alive with creatures whose size and form now seem almost impossible. And yet the evidence remains preserved in stone. The delicate wings of Meganeura, the segmented trails of Arthropleura, the armored shapes of ancient scorpions. Together, they reveal a simple but astonishing truth. Earth once supported insects and arthropods far larger than those that exist today. This realization raises a question that lingers quietly in the background. In the modern world, even the largest insects rarely grow beyond a few centimeters. The dragonflies that skim across lakes today are small compared to their ancient relatives. Millipedes hide beneath fallen leaves, their bodies no longer stretching across the forest floor. Something has clearly changed. The planet that once allowed insects to grow to such enormous sizes is not the same planet we live on now, which leads to a deeper mystery. If the fossils are telling the truth, and all evidence suggests they are, then something about the Earth itself once created the perfect conditions for these giants to exist. And understanding that difference means looking not only at the creatures preserved in stone, but at the ancient atmosphere that surrounded them. The fossils tell us that giant insects once existed. Stone preserves their wings, their tracks, even the delicate outlines of bodies that vanished hundreds of millions of years ago. Yet the fossils alone cannot explain why such creatures were possible. To understand that mystery, we must look not at the animals themselves, but at the air they lived in. Today, the atmosphere surrounding our planet contains about 21% oxygen. It is a balance that supports forests, animals, oceans, and the billions of organisms that share the Earth. We rarely think about it because it feels constant and dependable, but the atmosphere has not always been the same. During the Carboniferous Period, when giant arthropods ruled wetlands and skies, oxygen levels were far higher than they are today. Scientists studying ancient rocks and plant fossils estimate that oxygen may have reached concentrations close to 30, perhaps even 35% of the atmosphere. It is a difference that seems small at first glance, Yet for insects, it changes everything. Unlike mammals or birds, insects do not rely on lungs to breathe. They have no chest expanding and contracting to pull air into complex respiratory system. Instead, oxygen enters their bodies through tiny openings along their exoskeletons. From these openings, air travels through a branching network of internal tubes known as tracheae. These tubes spread throughout the insect's body, delivering oxygen directly to muscles and tissues. It is a simple and elegant system, but it comes with a limitation, because oxygen moves through these tubes mainly by passive diffusion. There is only so far it can travel effectively. In modern atmospheric conditions, this naturally limits how large an insect can become. As body size increases, oxygen has a harder time reaching the deepest tissues. Eventually, the system struggles to supply enough oxygen to sustain a larger body. In today's atmosphere, this invisible constraint quietly keeps most insects small. But the Carboniferous world played by different rules. With far more oxygen present in the air, diffusion became much more efficient. Oxygen molecules could travel deeper through the tracheal networks inside insect bodies. Muscles received more oxygen with less effort. Tissues that would normally struggle to breathe could function without difficulty. Under those conditions, insects gained an extraordinary advantage. Bodies that might have been impossible in the modern world suddenly became viable. Wings could grow wider, muscles could grow stronger, segmented bodies could stretch longer across forest floors. Generation after generation, natural selection shaped insects that were larger than anything alive today. The giants of that ancient age were not accidents. They were the natural result of a planet breathing differently. Dragonfly relatives with wingspans approaching 70 centimeters could glide across humid skies because the air itself supported them. Massive arthropods like Arthropleura could move through dense swamp forests because their bodies could absorb enough oxygen to sustain their enormous size. The atmosphere made it possible. In a quiet way, the air became the architect of the ecosystem. When we imagine prehistoric giants, we often picture evolution pushing animals toward greater size and strength. Yet the truth is more subtle. Evolution can only work within the boundaries that the environment allows. In the Carboniferous world, the environment allowed something extraordinary. For a time, the Earth itself created the perfect conditions for giant arthropods to thrive. But environments never remain unchanged. Atmospheres shift. Forests rise and fall. Climate patterns move slowly across continents. When those changes occur, the creatures that depend on specific conditions must adapt or disappear, which leads to an unsettling possibility. If the unusual atmosphere of the Carboniferous world allowed giant insects to evolve, then the disappearance of that atmosphere might explain why those giants eventually vanished as well. To understand why the air changed, the story must move deeper into the ancient landscapes that helped shape it, because the secret behind that oxygen-rich atmosphere did not begin in the sky. It began in the forests. To understand why the skies once held insects the size of birds, it is not enough to look upward toward the atmosphere. The story begins much closer to the ground, among forests that once stretched across the warm equatorial regions of an ancient Earth. These forests were unlike anything that exists today. If a traveller could step into one of these landscapes during the Carboniferous period, the first impression would be unfamiliar shapes rising from shallow water, instead of modern trees with spreading branches and leafy crowns. Towering plants stood like columns emerging from dark wetlands. Many belonged to a group known as lycopsids. Their trunks were tall and straight, sometimes reaching more than 30 meters into the humid sky. The bark covering them carried strange diamond-shaped patterns, the scars left behind by fallen leaves. From a distance, the forest might appear as endless rows of textured pillars disappearing into thick mist. Between these towering plants grew dense thickets of ancient horsetail relatives. These plants formed long segmented stalks that rose high above the swamp floor, some reaching heights of 20 meters or more. Their jointed stems and delicate branches created thick green walls that swayed slowly in the warm air. Water was everywhere. The ground beneath these forests remained permanently wet. Shallow pools and winding channels filled the spaces between roots. Fallen leaves and plant fragments drifted through dark water before settling into soft sediments below. The environment felt heavy and still. Warm temperatures and constant moisture wrapped the entire forest in a quiet humidity that rarely changed. Yet beneath this calm surface, something remarkable was happening. These forests were slowly transforming the atmosphere of the entire planet. Every leaf reaching toward the sun was performing a simple process known as photosynthesis. Using sunlight as energy, plants absorbed carbon dioxide from the air and released oxygen as a byproduct. It is a process so familiar that modern life depends on it without noticing. But in the Carboniferous world, this process was happening on an enormous scale. The vast swamp forests covered immense portions of the equatorial continents. Year after year, generation after generation, the plants pulled carbon dioxide from the atmosphere and replaced it with oxygen. Normally, when plants die, their remains decompose. Microorganisms break down the organic material, releasing carbon back into the air. But the wetlands of the Carboniferous period disrupted this cycle. In the deep, waterlogged soils of the swamps, oxygen was scarce beneath the surface. Fallen plants sank into mud where decomposition slowed dramatically. Instead of returning their carbon to the atmosphere, much of that plant material became buried beneath layers of sediment. Over millions of years, enormous quantities of carbon were locked underground. The buried remains of those ancient forests would eventually become the coal deposits that modern societies still mine today. But at the time, the process had a different consequence. With carbon being removed from the atmosphere and oxygen continuously released by living plants, the balance of gases in the air began to change. Slowly, almost invisibly, oxygen levels began to rise. What started as an ordinary biological process gradually reshaped the chemistry of the entire planet. The forests were not just ecosystems supporting plants and animals. They were vast environmental engines, quietly altering the atmosphere itself. As oxygen accumulated in the air, conditions emerged that had rarely existed before in Earth's history. Creatures breathing. That air began experiencing a world richer in oxygen than anything most modern organisms have ever known. Insects with their unique breathing systems were particularly sensitive to this change. As the forests expanded and oxygen levels climbed higher, the environment created new possibilities for life. Organisms that had once been limited by the physical constraints of their bodies suddenly found themselves in a world that allowed those limits to stretch. The forests were doing more than growing. They were preparing the stage for one of the strangest evolutionary experiments the planet had ever seen. Because as oxygen levels rose and ecosystems expanded across the Carboniferous world, evolution gained an opportunity it had rarely encountered before, and insects were among the first creatures ready to explore it. When the environment changes, evolution listens. Life on Earth is shaped by countless small pressures: temperature, food, predators, oxygen, space. For millions of years, these pressures quietly limit what creatures can become. Bodies grow only as large as their environment allows. Wings stretch only as far as energy and oxygen can sustain them. But occasionally, the rules loosen. During the Carboniferous period, the rising oxygen levels created a rare moment in the history of life. The atmosphere became richer. The wetlands expanded across entire continents, and ecosystems filled with opportunities waiting to be explored. In such moments, evolution begins to experiment. Insects were among the first creatures ready to take advantage of this new world. Their bodies were already built for rapid adaptation. Short life cycles allowed changes to appear quickly from one generation to the next. Small variations in size, wing structure, or strength could spread through populations in relatively short spans of time. As oxygen levels increased, the physical limitations that normally restrict insect growth began to weaken. Larger bodies became easier to sustain. Muscles could receive more oxygen. Wings could grow broader without exhausting the insect that carried them. The dense atmosphere above the wetlands offered gentle currents that helped support longer glides. Gradually, insects began exploring sizes that would have been impossible before. Some species developed wings capable of powerful, efficient flight. Wider wings meant greater lift. allowing insects to travel farther across the swamp forests while searching for food. The heavy air supported them as they glided between towering plants and across dark waterways. With larger bodies came stronger muscles. Predatory insects evolved mandibles capable of gripping prey in mid-air. Dragonfly-like hunters darted across the wetlands, their wings beating slowly, but with tremendous control. The skies of the Carboniferous world became filled with movement. Above the swamp forests, enormous insects cruised through warm air currents, watching for smaller creatures moving below. The open sky offered space rarely contested by other animals. With no birds or bats yet evolved, insects encountered little competition for aerial dominance. On the ground, other arthropods were experimenting with size in different ways. Thick exoskeletons protected their bodies as they moved through dense vegetation. Segmented forms allowed flexibility while supporting greater mass. Some species adapted to feed on decaying plant material that covered the swamp floor, turning the endless remains of fallen vegetation into energy for growth. Generation after generation, natural selection favored those individuals capable of surviving in this oxygen-rich world. Over millions of years, insects gradually pushed the boundaries of scale. The result was an ecosystem unlike anything that exists today. Dragonfly relatives glided through the sky with wings nearly 70 centimeters across. Massive arthropods crawled across the forest floor, with bodies longer than most modern reptiles. Entire food webs formed around creatures that modern ecosystems could never support. It was as if nature had opened a door and briefly allowed life to try something new. The Carboniferous forests became an evolutionary laboratory where scale itself was part of the experiment. But evolution rarely offers permanent victories. Every biological advantage depends on the stability of the environment that supports it. When conditions change, even the most successful creatures can find themselves facing new limits. The giants of the Carboniferous thrived because the world allowed them to exist. Yet the forces shaping the planet were already moving beneath the surface. The continents were drifting. Climates were shifting. Ecosystems were slowly evolving into forms that would not always favor enormous arthropods. The age of giant insects was rising toward its peak. But to fully understand why they thrived for so long, there is another part of the ancient world that must be considered. Not what existed within it, but what did not in the modern world. The sky is rarely empty. From dawn until nightfall, it is filled with movement. Birds cross continents on invisible highways of air. Swallows dart through warm evening currents. At night, bats sweep silently across fields, hunting insects beneath the moon. It is easy to assume the sky has always belonged to creatures like these. Yet during the Carboniferous period, the air above the forests held a very different story. If someone could stand within those ancient wetlands and look upward, they would see wide skies stretching above the towering plants. Warm air currents would drift slowly across the swamp, carrying mist and the scent of vegetation high above the canopy. But the shapes crossing that sky would look unfamiliar. There would be no flocks of birds circling overhead, no feathered silhouettes gliding across the clouds. As night approached, no bats would emerge from hidden roosts to sweep across the wetlands. For hundreds of millions of years after life first moved onto land, vertebrates had not yet conquered the air. Flight had evolved only once, and it belonged to insects. Long before birds evolved wings or mammals developed the ability to fly, insects had already mastered powered flight. Their lightweight bodies and flexible wings allowed them to rise above forests and wetlands, exploring a dimension of the environment that most other creatures could not reach. In the Carboniferous world, this ability gave them an extraordinary advantage. The sky was open. There were no aerial predators waiting above them, no larger flyers competing for food or territory. Vast layers of air stretched above the forests, with almost no competition at all. Evolution rarely leaves opportunities unused. Over time, insects expanded into this empty space with remarkable success. Their wings grew wider, their bodies stronger, their flight patterns more efficient. Dragonfly-like predators became some of the most impressive aerial hunters of the ancient world. Gliding above the swamp forests, they moved with quiet precision through the humid air. Their enormous wings caught gentle currents drifting above the canopy, allowing them to patrol large areas without exhausting their strength. Below them, countless smaller insects moved between the dense vegetation. The giant flyers watched patiently. When prey appeared, they could accelerate with surprising speed, snapping forward through the air with powerful wing beats. Their mandibles closed around insects drifting below, capturing them mid-flight before carrying them away. These predators were not merely large insects. They were the rulers of the ancient sky. Without birds to challenge them, they occupied the highest levels of the aerial food chain. Their presence shaped the behavior of countless smaller species moving through the wetlands below. Yet, despite the dominance of these giants, the skies of the Carboniferous world were strangely quiet. There were no flocks crossing the horizon, no constant chatter of birds moving through the trees. The air held long stretches of stillness broken only by the slow passage of enormous wings gliding overhead. It was a sky ruled by insects alone. For millions of years, this balance remained stable. Giant arthropods thrived above the forests while others moved slowly through the vegetation below. The environment supported them, and evolution continued refining their remarkable forms. From the perspective of those ancient ecosystems, the arrangement might have seemed permanent, but the Earth rarely holds any condition forever. Even while giant insects dominated the air, deeper forces were already reshaping the planet. Continents were drifting. Climates were shifting. The chemistry of the atmosphere itself would not remain unchanged. The Carboniferous world had reached one of the most extraordinary moments in its history. The age of giant arthropods stood at its peak. Yet hidden within the slow movements of the planet, the first signs of change had already begun. And in the chapters ahead, those changes would reveal some of the largest and most remarkable arthropods that ever lived, creatures that pushed the limits of size to astonishing extremes before their world quietly began to fade. As the Carboniferous world approached its peak, the forests and wetlands became home to creatures that would challenge even the imagination of modern observers. The scene settles over an ancient swamp at dusk. Warm mist drifts upward from dark pools of water. The towering plants of the forest lean slightly in the humid air, their immense trunks rising like columns from the saturated ground. Shadows gather beneath the tangled canopy, and the entire landscape moves with a slow, patient rhythm that has continued for millions of years. For a moment, the forest floor appears quiet, then something shifts within the undergrowth. At first, it looks like a fallen log slowly sliding across the damp soil. The shape is long and dark, partially hidden beneath layers of decaying leaves. But the movement continues, deliberate and steady, revealing something far more unusual than drifting wood. The object is alive. Segment after segment emerges from the vegetation, forming a massive body that stretches nearly 2 meters across the forest floor. Hard plates overlap along its back like armor, each segment moving smoothly with the next as the creature glides forward. This is Arthropleura, the largest land arthropod known to have ever lived. At a distance, the creature resembles an enormous millipede, though it belongs to a distinct ancient lineage that vanished long ago. Its body is composed of dozens of wide segments, each protected by thick plates that provide both strength and flexibility. As it moves through the damp forest floor, hundreds of legs hidden beneath its body work in quiet coordination, carrying the enormous creature forward with surprising grace. Despite its intimidating size, Arthropleura was likely not a predator. Fossil evidence suggests that it fed primarily on decaying plant material scattered across the swamp forests. Fallen leaves, rotting wood, and layers of organic debris provided endless nourishment in these wetlands. In a world where vegetation grew quickly and decomposition slowed beneath waterlogged soil, food was everywhere. The giant arthropod simply harvested what the forest provided. But Arthropleura was only one of many remarkable inhabitants of this ancient ecosystem. Above the swamp canopy, enormous dragonfly relatives glide through humid air currents. Their wings stretch wider than many modern birds, their delicate structures shimmering faintly as they patrol the skies for smaller insects moving between the towering plants. Along muddy shorelines, ancient scorpion-like predators explore the edges of shallow water. Their armored bodies move cautiously through tangled vegetation, searching for prey hidden among roots and fallen branches. Throughout the forest, countless insects move through leaves, water, and air. Some are small and delicate, while others are growing steadily larger as evolution experiments with the possibilities offered by this unusual world. It becomes clear that these creatures are not isolated curiosities. They belong to a fully functioning ecosystem built around arthropods of extraordinary scale. The forests support immense populations of insects feeding on vegetation and organic debris. Those insects provide food for larger predators that hunt both on the ground and in the air. Scavengers and decomposers break down the remains of plants and animals, returning nutrients to the wet soil beneath the swamp. Every part of the ecosystem is connected, and at the center of that system stand the arthropods. They dominate the forest floor, the tangled vegetation, and the humid skies above the canopy. For millions of years, their forms have shaped the structure of the entire environment around them. This was the age when arthropods ruled the land and the air alike. From the perspective of that ancient world, their presence would have seemed completely natural. Giant insects gliding across the sky or enormous segmented creatures crossing the forest floor were simply part of everyday life. Yet, to modern eyes, the scene feels almost impossible, because the ecosystems that allowed these creatures to exist have no true equivalent today. No modern forest shelters insects 2 meters long. No modern sky carries dragonflies the size of birds. Something about that distant world allowed life to reach sizes rarely seen before or since. And understanding those creatures raises a deeper and more intriguing question. How did bodies of such enormous scale actually function in the strange environment that created them? Creatures like Arthropleura and the enormous dragonfly relatives of the Carboniferous world appear almost unreal when viewed from a modern perspective. Their size seems to defy the quiet rules that shape the insects we see today. Yet, these giants were not accidents of nature. Their bodies were built according to the same biological principles that govern every arthropod on Earth. The difference lay not in entirely new anatomy, but in how familiar structures interacted with a very different environment. Unlike mammals, reptiles, or birds, arthropods do not carry their skeletons inside their bodies. Instead, they wear them. A rigid external shell, known as an exoskeleton, surrounds the soft tissues within. This protective armor supports the body, shields internal organs, and provides strong attachment points for muscles that move legs, wings, and mouth parts. The design is remarkably effective for smaller creatures. It allows insects to move quickly while remaining protected from predators and environmental hazards. But the system carries limitations. As an arthropod grows larger, its exoskeleton must grow thicker and heavier to support the increasing weight of the body inside. Each additional layer of armor adds strength, but also increases the energy required for movement. Breathing introduces another challenge. Arthropods do not rely on lungs to draw oxygen into the bloodstream. Instead, air enters through tiny openings along the body and spreads through networks of branching tubes known as trachea. Oxygen moves through these tubes mainly by diffusion, gradually reaching the tissues that require it. In the modern atmosphere, this system quietly limits how large most insects can become. As body size increases, oxygen must travel farther to reach deeper tissues, and the efficiency of diffusion begins to decline. Eventually, the body simply becomes too large for the system to supply enough oxygen. But the Carboniferous world altered that balance. With far more oxygen present in the atmosphere, diffusion worked far more effectively. Oxygen molecules could travel deeper into tissues without struggling against the usual limitations. The internal tracheal systems of arthropods became far more efficient than they would be today. Under those conditions, larger bodies could function without suffocating. Meanwhile, the environment surrounding those creatures offered additional support. The humid atmosphere of the Carboniferous forests reduced the risk of dehydration, a constant challenge for animals protected only by thin openings in their shells. Moist air and waterlogged soil created stable conditions where large arthropods could move without losing vital moisture too quickly. Even flight behaved differently in that ancient sky. Dragonfly relatives such as Meganeura carried enormous wings that spread wide across the humid air. Those wings likely allowed them to glide for long stretches. Using gentle air currents above the swamp forests, to conserve energy rather than beating their wings continuously. These giant flyers may have relied on slow, powerful strokes followed by long periods of gliding. The dense atmosphere would have supported their weight, making sustained flight easier than it might seem today. On the forest floor, creatures like Arthropleura thrived in an entirely different way. The thick layers of decaying vegetation covering the swamp ground created a soft, sheltered environment. Fallen leaves and plant fragments formed endless food supplies for large arthropods, feeding on organic debris. Hidden beneath dense vegetation and protected by constant humidity, these massive segmented creatures could move slowly through their world with little threat from predators. Everything about their environment supported their unusual size. Their breathing systems functioned efficiently. Their bodies remained hydrated. Their food sources were abundant and easy to reach. The giants of the Carboniferous were not clumsy monsters wandering through a hostile landscape. They were perfectly suited to the world around them. Their bodies were tuned precisely to the conditions that surrounded them. Yet that harmony depended on something fragile. It required the environment to remain stable. Atmospheric oxygen needed to stay high. The forests needed to remain wet and expansive. The climate needed to preserve the delicate balance that allowed these creatures to function. If those conditions changed even slightly, the advantages that allowed giant arthropods to thrive could begin to disappear. And while these creatures ruled their ancient ecosystems, evolution was already working quietly in the background. Because somewhere within that same world, new forms of life were beginning to appear, creatures built in ways that would eventually challenge the dominance of the giants. For millions of years, the Carboniferous forest seemed to belong entirely to the arthropods. Giant dragonfly relatives ruled the warm skies above the wetlands. Massive, segmented creatures moved slowly across the forest floor. Countless insects filled the air, the water, and the dense vegetation between towering plants. To an observer standing within that ancient landscape, the dominance of arthropods might have appeared permanent, but the story of life on Earth rarely stands still. Even while giant insects flourished, evolution was quietly exploring new possibilities beneath the canopy of the swamp forests. Among the creatures moving cautiously through this ancient world were the early ancestors of reptiles. At first, they were small and easily overlooked. Their bodies were slender, their movements careful as they navigated between roots and fallen vegetation. Compared to the enormous arthropods around them, these early vertebrates seemed almost insignificant. Inside their bodies were features that carried extraordinary potential. Unlike amphibians, which depended on water to reproduce, these emerging reptiles possessed a new evolutionary innovation, the protective ECG. Encased within durable shells, reptile eggs could develop safely away from open water. The embryos inside carried their own tiny aquatic environments, allowing them to grow without needing ponds or swamps to survive. This single adaptation opened new territories. While amphibians remained tied to the wetlands where their eggs could remain moist, reptiles began venturing beyond the dense swamp forests. They explored drier ground where towering plants gave way to more open landscapes. At first, the change seemed subtle. The reptiles were still small. They moved cautiously across the edges of the Carboniferous forests, feeding on insects and smaller creatures hidden within vegetation. Meanwhile, the arthropods remained dominant. The skies still belonged to giant dragonflies. The forest floor still trembled beneath the slow movement of enormous segmented bodies. The wetlands continued to support ecosystems, built around creatures that had ruled the land for millions of years. But evolution rarely reveals its intentions immediately. Inside the bodies of these small reptiles were traits that would eventually reshape life on land. Their internal skeletons allowed muscles to grow stronger and more flexible than those supported by external shells. Their lungs could actively draw air into the body, delivering oxygen through circulatory systems far more efficient than the diffusion-based breathing of arthropods. Over time, these advantages would allow vertebrates to grow larger without facing the same biological limits that constrained giant insects. Their bodies could support weight differently. Their breathing could adapt more easily as environmental conditions changed. For now, those advantages remained hidden within small and cautious animals moving quietly through the shadows of the forest. The arthropods still ruled the world, but evolution had begun preparing something new. Across generations, reptiles slowly diversified into different shapes and behaviors. Some became stronger hunters. Others adapted to new habitats forming along the edges of the ancient wetlands. The changes were gradual, almost invisible when measured against the immense timescales of geological history. Yet the balance of life on land had begun to shift. Not with a sudden collapse or dramatic battle for dominance, but through a slow expansion of new possibility. While giant arthropods continued thriving in their humid forests, the planet was quietly producing creatures capable of surviving in environments those giants could never fully control. The seeds of a future world were already growing, and the forces shaping that future were not limited to the evolution of new animals. Far beneath the surface of the Earth, the planet itself was beginning to move in ways that would eventually transform the entire environment. When those changes arrived, they would test the stability of the arthropod empire more severely than any new competitor could, because the greatest threat to the giants was not another animal. It was the changing world itself, and in the next chapter, the slow turning of the planet would begin to reveal how fragile even the most dominant ecosystems can become. From a human point of view, the Earth feels steady and dependable. Mountains seem permanent. Oceans hold their places. Forests grow, change with the seasons, and return again the following year. Even the climate, though sometimes unpredictable, appears to follow familiar patterns. It is easy to imagine the planet as something fixed beneath our feet. Yet the Earth is anything but still. Beneath the forests, oceans, and continents lies a restless surface broken into enormous pieces known as tectonic plates. These plates move slowly across the planet's mantle, drifting over immense spans of time. The movement is so gradual that it escapes human perception, yet over millions of years it reshapes the entire surface of the world. During the late Carboniferous Period, this slow motion had already begun to change the arrangement of the continents. Land masses that had once been separated by shallow seas were drifting steadily toward one another. The movement was measured in centimeters each year, barely noticeable within the lifetime of any creature living at the time. But geological time does not measure years. It measures millions of them. Over those immense spans, the wandering continents gradually gathered together. This long journey would eventually produce one of the most famous land formations in Earth's history, the supercontinent known as Pangaea. At the time, however, the process had only just begun. As the continents drifted closer, the geography of the planet slowly transformed. Mountain ranges rose where plates pressed against one another. Vast inland regions expanded far from the moderating influence of oceans. With geography changing, climate began to shift as well. The Carboniferous world had once been dominated by warm, humid environments where vast swamp forests thrived. Rain fell regularly across the equatorial regions, feeding the wetlands that supported giant arthropods and the enormous plants surrounding them. But as the continents continued moving, those patterns slowly changed. Some regions that had once remained permanently wet began experiencing seasonal variations in rainfall. Periods of dryness began appearing where steady humidity had once prevailed. Rivers altered their paths as landscapes shifted beneath them. At first the changes were subtle. A swamp that had remained flooded year-round might begin drying slightly during certain seasons. Forests that once spread endlessly across the wetlands might become divided by areas of firmer ground. No single generation of creatures could notice the difference. To the giant insects gliding above the forests, the world still seemed familiar. The air remained warm, the wetlands still stretched across the land, and food remained abundant. Yet beneath the surface, the environment was quietly evolving. Over thousands and then millions of years, the vast Carboniferous forests began to fragment. Some wetlands shrank while others disappeared entirely. New landscapes formed where water once stood. The ecosystems that had supported giant arthropods for ages were beginning to change, and because those creatures depended heavily on stable conditions, high humidity, dense vegetation, and oxygen-rich air. They were among the first organisms sensitive to even small environmental shifts. None of this happened suddenly. There were no dramatic storms or catastrophic events marking the beginning of the transformation. Instead, the planet simply continued doing what it had always done, moving slowly through cycles of change, from the perspective of any creature living within those forests. The environment still felt constant, but the deeper forces shaping the Earth were already rewriting the future. The world of giant insects appeared stable and enduring, yet the ground beneath them was slowly drifting toward a different arrangement of continents and climates. And as these shifts continued, one of the most important changes unfolding across the planet involved something invisible, not the movement of land, but the chemistry of the air itself. While continents drifted and climates slowly shifted, another transformation was unfolding above the forests, hidden within the air itself. For millions of years during the Carboniferous Period, oxygen levels had remained unusually high. The vast swamp forests continuously released oxygen through photosynthesis, while enormous quantities of plant material were buried beneath waterlogged sediments. The atmosphere had gradually become richer in oxygen than at almost any other time in Earth's history. It was this invisible abundance that had quietly supported the giants of the arthropod world. But atmospheres are not fixed systems. Just as the continents move and climates evolve, the chemistry of the air changes as well. As geological forces reshaped the planet and ecosystems shifted across the continents, the balance between oxygen and other gases slowly began to adjust. The immense swamp forests that once covered wide regions were no longer expanding at the same pace. Some areas became drier, reducing the accumulation of plant material that had once trapped carbon beneath layers of sediment. Meanwhile, geological activity continued influencing the atmosphere in subtle ways. Volcanic processes released gases from deep within the Earth, altering the delicate balance that had previously allowed oxygen to rise. Over immense spans of time, the oxygen-rich atmosphere of the Carboniferous world began to decline. The change was gradual. From one generation to the next, the difference would have been almost impossible to notice. The air still felt warm and breathable. The forests still stretched across large regions of the planet, but the invisible chemistry of the atmosphere was shifting. For many organisms, this change had little immediate impact. Animals with lungs and circulatory systems could adapt to moderate variations in oxygen without major difficulty. Their bodies actively moved oxygen through blood, allowing them to function across a range of atmospheric conditions. But giant arthropods lived under different rules. Their breathing system relied almost entirely on passive diffusion through networks of internal tubes. Oxygen entered their bodies through small openings and slowly spread through branching channels until it reached the tissues that needed it. This system worked remarkably well in oxygen-rich air. Yet, as oxygen levels slowly declined, the efficiency of that process began to weaken. For smaller insects, the difference was manageable. Their compact bodies allowed oxygen to travel short distances through the tracheal system. Even with slightly lower oxygen concentrations, their tissues could still receive the oxygen they required. But for larger arthropods, the challenge was far greater. In massive bodies like those of Arthropleura or the giant dragonfly relatives gliding above the forests, oxygen needed to travel much farther to reach the deepest tissues. As atmospheric oxygen slowly decreased, the diffusion process became less efficient. Muscles that once received abundant oxygen now had to work harder to obtain it. Large bodies required more energy simply to function. Over many generations, these subtle limitations began to shape evolution itself. Natural selection quietly favored individuals that required less oxygen to survive. Smaller bodies became easier to sustain in the changing atmosphere. Creatures that demanded less oxygen could grow, move, and reproduce more successfully than their larger relatives. The giants of the Carboniferous world had once thrived in an atmosphere perfectly suited to their needs. Now that same atmosphere was becoming less accommodating. The very force that had allowed insects to reach extraordinary sizes was slowly turning against them. This shift did not bring immediate extinction. Giant arthropods continued living within the forests for long stretches of time. But their evolutionary advantage had begun to weaken. The balance of the ecosystem was changing. What had once been an ideal world for enormous insects was gradually becoming a world that favored smaller and more adaptable forms. It marked a quiet turning point in Earth's history. The environmental conditions that had produced the age of giant arthropods were beginning to disappear. And while the atmosphere continued changing, another transformation was unfolding across the planet, one that would reshape life on land even more dramatically than the slow decline of oxygen in the air. For millions of years, the Carboniferous forests had covered vast stretches of the planet. Warm wetlands extended across equatorial continents, their towering plants forming dense green worlds where humidity rarely faded and water filled nearly every hollow in the ground. These forests had created the conditions that allowed giant arthropods to flourish. They produced the oxygen, rich atmosphere. They covered the forest floor with thick layers of decaying vegetation. They held moisture in the air and soil, protecting creatures whose bodies depended on constant humidity. But the forests themselves were not immune to change. As continents continued drifting and climates slowly shifted, the delicate balance that sustained the great wetlands began to weaken. Regions that had once remained permanently wet began experiencing new patterns of rainfall. Seasons emerged where steady humidity had once prevailed. In some places, periods of dryness began appearing between the rains. At first, the changes were subtle. A swamp that had once remained flooded throughout the year might begin to dry slightly during certain months. Shallow pools shrank, exposing patches of soil that had long been hidden beneath water. Plants that depended on constant flooding struggled to adapt. Gradually, the endless wetlands that had once stretched across continents began breaking apart. Some forests remained dense and humid, but others thinned or disappeared entirely. The towering lycopsid plants that had dominated the swamps could not always survive in soils that dried too often. Without the constant saturation they required, many of these ancient plants began declining. As the forests fragmented, the ecosystems they supported began changing as well. The thick carpets of decaying vegetation that once covered the swamp floor became less common. Fallen plant material that had previously accumulated beneath waterlogged conditions now dried and decomposed more rapidly in exposed environments. For large arthropods, these changes carried serious consequences. Their bodies depended heavily on moist environments. The openings along their exoskeletons through which oxygen entered their breathing systems also allowed water to escape. In constantly humid forests, this was rarely a problem, but in landscapes growing drier and more variable, dehydration became a growing risk. The protected world that had allowed enormous arthropods to move comfortably across the forest floor was slowly disappearing. At the same time, the changing environment opened new opportunities for other animals. Where wetlands retreated, firmer ground emerged. Plants better adapted to drier conditions began spreading across the landscape. These new environments proved more suitable for reptiles and other vertebrates that could tolerate fluctuating humidity and temperature. Creatures with internal skeletons and efficient lungs could explore areas where giant arthropods struggled to survive. The shift did not happen in a single dramatic moment. There was no sudden collapse that ended the Carboniferous forests overnight. Instead, the transformation unfolded gradually across immense spans of time. Wetlands shrank here, expanded there, and vanished elsewhere. Some regions still supported the familiar swamp ecosystems, while others evolved into entirely new landscapes. To the creatures living within those forests, the world would have seemed mostly familiar from one generation to the next. Yet, over millions of years, the environment was quietly becoming something different, and as the forests continued changing, the delicate network of conditions that supported giant arthropods began unraveling. The humid landscapes that had once sheltered them were fading. The endless vegetation that had fed them was thinning. The age of giant insects was entering its final phase. Their decline did not come through sudden catastrophe, but through the slow disappearance of the world that had created them. The forests that had given rise to the giants were vanishing, and with them the stability that had allowed enormous arthropods to dominate the land and skies for millions of years. In the chapters that follow, the mystery deepens, because the disappearance of these giants would not happen all at once, and the reasons behind their final decline are far more complex than they might first appear. By the closing chapters of the Carboniferous and the early rise of the Permian world, the planet that had once nurtured enormous arthropods was beginning to transform. The change did not arrive with storms or sudden catastrophes. Instead, it unfolded slowly, almost gently, spreading across the landscape in ways that no single creature could fully perceive. If one could return to those ancient forests again, the familiar wetlands would still be there. Towering plants still reached upward through warm air. Pools of dark water still reflected the sky between thick walls of vegetation. Yet something subtle had shifted. The forests no longer stretched endlessly across the land as they once had. In many regions, the wetlands were beginning to break apart, forming patches of dense forest, separated by areas of firmer ground. The landscape felt less continuous, less saturated with water than it had for millions of years. Rivers that once overflowed their banks year-round began following quieter rhythms. During wetter seasons they spread across the floodplains, but at other times their waters pulled back into narrow channels. The soil, once permanently soaked, occasionally hardened beneath the sun. The air itself seemed slightly different. Humidity still lingered beneath the forest canopy, but the heavy mist that had once hung constantly above the wetlands was beginning to thin. Warm winds occasionally carried drier air across regions that had once remained wrapped in moisture. None of these changes appeared dramatic when viewed in isolation. To the creatures living within those forests, the world still seemed mostly familiar. Giant dragonflies still glided across open water. Massive arthropods still moved through thick vegetation. Life continued as it had for countless generations. But beneath the quiet rhythms of the forest, the forces shaping the earth were continuing their slow work. The continents were drifting steadily toward one another, forming the early stages of the vast supercontinent that would later be known as Pangaea. As these landmasses merged, the arrangement of oceans and mountains changed as well. Those changes altered global climate patterns. Regions that had once remained permanently tropical began experiencing subtle shifts in temperature and rainfall. Some areas that had supported endless swamps gradually became drier landscapes, where water no longer gathered as easily. The transformation unfolded across immense spans of time. Over millions of years, the great Carboniferous wetlands slowly shrank. Forests fragmented into smaller patches, and the environments that had once remained stable began fluctuating with changing seasons. For giant arthropods, these shifts presented a growing challenge. Their bodies depended heavily on moisture. The openings along their exoskeletons allowed oxygen to enter their tracheal breathing systems, but they also allowed water to escape. In constantly humid environments, dehydration was rarely a concern. But in landscapes where humidity weakened, that balance became more fragile. At the same time, oxygen levels in the atmosphere were no longer as high as they had been during the height of the Carboniferous forests. The invisible advantage that had once allowed enormous arthropods to thrive was slowly fading. Large bodies required more oxygen to sustain their tissues and muscles. As oxygen concentrations declined, maintaining those bodies became increasingly difficult. Evolution responded quietly. Within populations of giant insects and other arthropods, individuals with slightly smaller bodies required less oxygen and less energy to survive. Over many generations, natural selection gradually favored these smaller forms. The giants did not disappear overnight. They continued moving through the forests for long stretches of time, but their numbers slowly declined, generation after generation, as the environment grew less suited to their extraordinary size. From the perspective of the ancient forests, the change might have seemed almost invisible, but when viewed across the immense timeline of Earth's history, something significant was happening. The empire of giant arthropods, the age when enormous insects ruled the skies and forests, was beginning to fade. The world that had once sustained them was quietly becoming something else. And as those giants struggled to adapt to a changing planet, another group of animals was slowly expanding its place on land creatures whose bodies were built to thrive under conditions that arthropods could never fully master. While the giants of the arthropod world struggled quietly with a changing environment, another story was unfolding across the land. At first it was easy to overlook. Small animals moved cautiously between roots and fallen vegetation at the edges of the ancient forests. Their bodies were low to the ground, their movements deliberate as they searched for food among insects and smaller creatures. These were early reptiles. Compared with the enormous arthropods that still roamed the wetlands, they appeared insignificant. They were smaller, less numerous, and far from dominant in the ecosystems of the time. Yet inside their bodies were features that carried extraordinary promise. For hundreds of millions of years before this moment, vertebrate animals on land had been limited by one crucial requirement. Amphibians, the dominant land vertebrates of earlier ages, still depended on water to reproduce. Their soft eggs required moisture to survive, which meant they could not stray far from ponds, rivers, or swamps. But reptiles had evolved something different. Their eggs were enclosed in protective shells, creating small self-contained environments where developing embryos could grow safely away from open water. Inside each egg was a tiny world that carried the moisture and nutrients needed for early life. This innovation changed everything. For the first time, vertebrates could reproduce on dry land without depending on wetlands. They were free to explore environments far beyond the ancient swamp forests. As climate shifted and landscapes slowly dried, reptiles followed the opportunities opening before them. They moved across firmer ground where amphibians struggled to survive. They explored areas where the soil no longer remained permanently soaked. Gradually, they spread through regions that giant arthropods rarely occupied. Their bodies offered other advantages as well. Unlike arthropods, reptiles carried their skeletons inside their bodies. These internal frameworks supported powerful muscles that allowed flexible movement across uneven terrain. Instead of relying on rigid exoskeletons, their bodies could grow larger while maintaining strength and agility. Their breathing systems also worked differently. Where giant insects depended on passive oxygen diffusion through networks of internal tubes, reptiles used lungs that actively drew air into the body. Oxygen traveled through the bloodstream, reaching tissues efficiently even when atmospheric oxygen levels fluctuated. As the ancient atmosphere slowly changed, this advantage became increasingly important. Reptiles could remain active and mobile even as oxygen levels declined from the unusually high concentrations of the Carboniferous world. Their bodies were less restricted by the environmental conditions that limited giant arthropods. At first, these differences did not immediately shift the balance of power. The wetlands still belonged largely to the arthropods. Giant dragonflies continued gliding through humid skies. Massive segmented creatures still moved slowly across forest floors, rich with decaying vegetation. But the reptiles were spreading. Across the early Permian landscapes, small reptilian predators began appearing in greater numbers. They hunted insects among vegetation, slipped across rocky ground, and explored territories that had once been inhospitable to vertebrate life. Their presence marked the beginning of something new. For hundreds of millions of years, arthropods had dominated life on land. Their bodies and breathing systems had once matched the conditions of the ancient world perfectly. But the planet was changing, and in that changing world, vertebrates carried advantages that would slowly reshape terrestrial ecosystems. The reptiles moving quietly through those forests were not yet rulers of the land. They were still small, still cautious, still overshadowed by the giants around them. Yet evolution was quietly preparing them for a different future. The rise of vertebrates had begun, but the fate of the giant arthropods would not be decided by competition alone. Far deeper forces were already gathering beneath the surface of the planet, forces that would soon reshape the entire living world. As the Permian world unfolded, the slow changes that had begun during the final years of the Carboniferous continued to spread across the planet. Landscapes that had once seemed stable were gradually transforming, and the effects of those changes could now be felt across both land and sea. The continents were still drifting toward one another, steadily assembling into the vast landmass that would eventually be known as Pangaea. As this supercontinent formed, enormous interior regions developed far from the cooling influence of the oceans. These inland territories experienced stronger seasonal extremes than the wetlands that had once dominated the equatorial world. Summers grew hotter, dry seasons lasted longer, rainfall patterns shifted in ways that slowly reshaped ecosystems. Forests that had once thrived in constant humidity struggled to survive under these changing conditions. Wetlands that had supported dense vegetation began shrinking into smaller, scattered environments. The creatures that depended on those wetlands were feeling the pressure. giant arthropods once perfectly suited to humid forests and oxygen-rich air, now lived in ecosystems that were becoming less predictable. The decline of the great swamp forests reduced the stable environments they needed to maintain their enormous bodies. At the same time, atmospheric oxygen levels continued drifting downward from their ancient peaks. The invisible advantage that had allowed arthropods to reach extraordinary sizes was gradually fading. But the changing climate and atmosphere were only part of the story. Far beneath the surface of the Earth, forces were building that would soon push the planet toward one of the most dramatic turning points in its history. Deep within the crust, molten rock was rising. In the region that would one day become Siberia, vast reservoirs of magma were gathering beneath the surface. Pressure built slowly as heat from the Earth's interior forced enormous volumes of molten material upward. Eventually, the crust could no longer contain the rising magma. What followed would become one of the largest volcanic events ever known. Across a region covering millions of square kilometers, volcanic eruptions began breaking through the surface of the Earth. Rivers of lava poured across the land, spreading layer after layer of basalt rock across the ancient landscape. These eruptions did not last for days or months. They continued for thousands of years. With every eruption, enormous quantities of gases escaped into the atmosphere. Carbon dioxide, methane, and other volcanic emissions spread across the sky, gradually altering the delicate balance of the planet's climate. The consequences reached far beyond the volcanic fields themselves. As greenhouse gases accumulated, global temperatures began to rise. Oceans warmed and lost oxygen. Weather patterns shifted across continents, already struggling with environmental change. Ecosystems everywhere were pushed toward instability. For giant arthropods, the situation grew increasingly difficult. Their bodies had evolved for a world of humid forests and oxygen, rich air. But that world was slowly disappearing beneath rising temperatures, shifting climates, and declining oxygen levels. The pressures that had already begun weakening the giant arthropod populations now intensified. Yet the coming crisis would not affect them alone. The changes unfolding across the planet threatened nearly every ecosystem on Earth. Life on land and in the oceans was approaching a moment unlike anything it had experienced before. The age of giant insects was not ending because of a single disaster. It was ending because the planet itself was entering a period of profound transformation. While animals struggled to adapt to a changing world, the Earth was preparing one of the greatest catastrophes in its long history. And in the next chapter, that catastrophe would reveal itself in full, an event so severe that it nearly erased life from the planet entirely. Around 252 million years ago, the Earth entered one of the most dangerous chapters in the entire story of life. By this time, the Permian world had already been shifting for millions of years. Forests had thinned in many regions. The atmosphere had slowly changed. New animals were spreading across the land while others quietly declined. But none of those earlier changes prepared the planet for what would come next. In a region that is now part of northern Asia, the ground began to split open. The crust of the Earth fractured across enormous distances, releasing molten rock from deep within the planet. What followed was not a single volcanic eruption, but a chain of eruptions on a scale rarely seen in geological history. Across what is now Siberia, lava poured from the Earth in vast sheets. Rivers of molten rock spread across the landscape, covering forests, rivers and plains beneath layers of burning stone. These eruptions would eventually create one of the largest volcanic formations on Earth, now known as the Siberian Traps. The word traps comes from an old term describing stair-like layers of rock, and that is exactly what these eruptions left behind. Enormous terraces of basalt formed as one layer of lava cooled and another flowed over it. But the lava itself was only part of the story. Each eruption released vast quantities of gases into the atmosphere. Carbon dioxide poured from the volcanic vents. Methane escaped from heated sediments deep underground. Toxic compounds drifted through the air, spreading far beyond the volcanic region itself. For thousands of years, these gases continued entering the atmosphere. Slowly, the chemistry of the planet began to change. As greenhouse gases accumulated, global temperatures rose. Heat spread across continents and oceans alike. Climate systems that had already been unstable now shifted more dramatically. Oceans began warming to levels that many marine organisms could not tolerate. As water temperatures increased, oxygen dissolved in the seas became scarcer. Entire marine ecosystems began collapsing. Coral reefs vanished. Many ancient fish species disappeared. Creatures that had dominated the oceans for millions of years suddenly vanished from the fossil record. The devastation in the oceans spread outward through food chains. Predators lost their prey. Filter feeders lost the plankton they depended on. Ecosystems that had once been stable for ages began unraveling. On land, the crisis was just as severe. Extreme heat waves swept across continents. Forests weakened or disappeared entirely in many regions. The animals that depended on those forests struggled to find food and shelter. As ecosystems broke down, food chains collapsed. Herbivores lost the plants they depended on. Predators lost their prey. Entire communities of organisms vanished from one generation to the next. The scale of the catastrophe was almost unimaginable. Today, scientists estimate that roughly 90% of marine species disappeared during this extinction event. On land, nearly 70% of known species vanished. It was the most devastating biological collapse the planet had ever experienced. Life itself came dangerously close to unraveling. For long stretches of time during this crisis, ecosystems across the planet were reduced to scattered survivors, struggling to endure in harsh environments. Some scientists believe that at certain moments during this period, life on Earth approached the edge of total collapse. Yet, even in the midst of this catastrophe, a few resilient species managed to survive. Small, adaptable organisms endured where larger and more specialized creatures could not. The Great Extinction did not eliminate life entirely, but it reshaped the planet in ways that would echo through every chapter of evolution that followed. For giant arthropods, however, the consequences were devastating. The crisis did not simply threaten their survival. It erased the environmental conditions that had once allowed them to exist at all. As the extinction crisis deepened, life across the planet struggled to endure conditions that had never existed before. Oceans warmed and lost oxygen. Forests thinned or vanished in many regions. Climate patterns shifted rapidly under the influence of volcanic gases and rising temperatures. For giant arthropods, these changes created challenges their bodies were never built to overcome. Their enormous size had once been an advantage. In the oxygen-rich atmosphere of the Carboniferous world, their breathing systems functioned efficiently. Large wings carried them through humid skies. Massive segmented bodies moved comfortably through dense forests where food and moisture were abundant. But those advantages depended entirely on a stable environment. As the volcanic eruptions continued and the planet's atmosphere changed, oxygen levels began falling more sharply. The delicate balance of gases that had once supported giant insects slowly collapsed under the weight of volcanic emissions and shifting ecosystems. For animals with lungs and circulatory systems, lower oxygen levels presented difficulties, but not impossibilities. Vertebrates could draw air into their lungs and deliver oxygen through blood to the tissues that needed it. Giant arthropods lived under different rules. Their bodies relied on passive diffusion to deliver oxygen through networks of internal tubes. Oxygen entered through small openings in their exoskeletons and traveled gradually through branching tracheal passages. This system worked well when oxygen was abundant, but as oxygen concentrations dropped, diffusion became far less effective. Large bodies required oxygen to travel greater distances to reach deep tissues. Muscles that once received ample oxygen now struggled to function. The larger the arthropod, the more severe the limitation became. Creatures that had once soared through humid skies or crawled across dense forests found themselves living in an atmosphere that could no longer sustain their size. Smaller insects, however, were far more resilient because their bodies were compact. Oxygen only needed to travel short distances within their tracheal systems. Even in a changing atmosphere, these smaller creatures could still receive enough oxygen to survive and reproduce. Generation after generation, natural selection favored these smaller forms. At the same time, the collapse of ecosystems created another challenge for the giants. The forests that had once covered vast regions were disappearing under rising temperatures and shifting climates. Wetlands dried, vegetation declined, the thick layers of decaying plant material that had once fed giant arthropods became scarce. Without stable forests and abundant moisture, the habitats that supported large arthropods simply vanished. Creatures that had evolved for humid environments struggled to survive in landscapes growing hotter and drier. Their bodies lost water more quickly. Food became less predictable. Safe habitats grew smaller with every passing generation. The giants of the ancient world had been shaped perfectly for the Carboniferous environment. Their size, their breathing systems, their lifestyles, all had evolved for a planet with high oxygen, vast forests, and stable climates. When those conditions disappeared, the traits that once made them successful became obstacles to survival. They had not been defeated by predators. They had not lost a battle against another species. Instead, the planet itself had changed the rules of the environment they depended on. And when those rules changed, the age of giant arthropods quietly came to an end. The skies no longer held dragonflies with wings the size of birds. The forest floor no longer trembled beneath the slow movement of massive segmented creatures. The giants faded from the world they once dominated. Yet even in the midst of this devastating extinction, life did not vanish entirely. Some organisms endured the crisis small. Adaptable survivors remained scattered across the changing landscapes, and from those survivors the next chapter of Earth's history was about to begin. When the long wave of destruction finally began to subside, the Earth that remained looked nothing like the world that had existed before. The Great Extinction had not passed quickly. For thousands of years the planet endured unstable climates, poisoned oceans, and collapsing ecosystems. Life retreated again and again, searching for pockets of stability in an environment that had become increasingly hostile. Eventually, the worst of the volcanic activity slowed. The atmosphere began to settle. Temperatures remained high in many regions, but the relentless chaos that had defined the crisis began to ease. What remained was a wounded planet. Across vast stretches of land, forests had vanished. In many places the ground lay bare beneath an unforgiving sky. Rivers still flowed, but their surrounding ecosystems were sparse and unfamiliar. The rich wetlands of the Carboniferous world were gone. The towering plants that had once filled those swamps had disappeared or been replaced by simpler vegetation struggling to reclaim the land. Yet even in this broken landscape, life had not vanished completely. Scattered across the planet were small communities of survivors, organisms capable of enduring conditions that had destroyed countless others. Among them were insects, not the enormous forms that once ruled the skies, but smaller, more adaptable species. Their compact bodies required less oxygen, less food, and less stable environments. Where the giants had struggled, these smaller insects could continue living. They moved through the recovering landscapes quietly, feeding on whatever resources remained available. Microbial life proved even more resilient. Invisible to the eye, bacteria and other microorganisms endured in soils, waters, and sediments across the planet. These tiny organisms played a crucial role in rebuilding ecosystems, recycling nutrients, and slowly restoring the biological foundations of life. And among the vertebrates, reptiles continued their quiet expansion. Many amphibian species had vanished during the extinction, unable to survive the dramatic environmental changes. But reptiles possessed advantages that allowed them to persist in drier, less stable conditions. Their protective eggs no longer tied them to wetlands. Their lungs allowed them to remain active even as oxygen levels fluctuated. Their internal skeletons supported movement across new landscapes where arthropods had once dominated. In the years following the extinction, reptiles slowly diversified. Small predators hunted insects across recovering plains. Other species adapted to new food sources appearing within emerging ecosystems. What had once been a world shaped primarily by arthropods was beginning to evolve into something entirely different. This pattern appears again and again throughout Earth's history. Mass extinctions rarely erase life completely. Instead, they act as enormous resets. Dominant groups vanish, opening space for survivors that might previously have been small or insignificant. Freed from competition, those survivors expand into the empty ecological roles left behind. The Permian extinction was the most devastating of these resets, but it also cleared the path for a new chapter of evolution. The giant arthropods that once ruled forests and skies were gone. Their time had ended with the disappearance of the world that created them, yet insects themselves endure. Smaller species spread across recovering landscapes, adapting to environments very different from the humid wetlands of the Carboniferous. Meanwhile, reptiles continued evolving into new forms that would eventually dominate life on land. From the ruins of extinction, a new biological world was slowly assembling itself. It would take millions of years for ecosystems to fully recover. But evolution was already moving forward, and the creatures that survived this catastrophe would give rise to the next great age of life on Earth, an age in which vertebrates, not arthropods, would shape the future of the planet. When the long storm of extinction finally passed, the Earth entered a quiet and uncertain chapter of its history. The Permian-Triassic catastrophe had reshaped nearly every ecosystem on the planet. The oceans had lost most of their species. Forests that once covered continents had vanished or been reduced to scattered remnants. Entire groups of organisms that had dominated life for millions of years were suddenly gone. What remained was a world that felt strangely empty. Across the recovering continents, vast stretches of land lay open beneath a hazy sky. Rivers still carved their paths across the plains, but their banks were no longer lined with dense vegetation. In many regions, the soil appeared exposed and fragile, waiting for life to return. The air itself still carried the lingering effects of the volcanic eruptions that had shaken the planet. Temperatures were higher than before. Weather patterns were unstable. The familiar balance that had once shaped ancient ecosystems had not yet fully returned. If someone could have travelled across the Earth during this time, they would have witnessed landscapes that felt unfinished. Patches of plants struggled to reclaim the ground. Thin forests appeared in sheltered valleys while vast plains remained sparsely covered. The planet seemed to be recovering slowly, as though life itself was cautiously rebuilding the world. Yet even within this quiet aftermath, movement continued. Small insects crawled through the scattered vegetation. Their bodies were modest in size compared to the giants of earlier ages, but they carried the resilience that had allowed them to survive the catastrophe. They fed on the first returning plants, on organic debris left behind by the extinction, and on each other. Nearby, early reptiles moved across the open terrain. These animals were still relatively small, yet their presence hinted at a future that had not yet fully arrived. They explored landscapes where forests were still forming, hunting insects and other small creatures among the recovering ecosystems. Together, these survivors formed the fragile beginnings of a new biological world. The rebuilding of life after a mass extinction does not happen quickly. Ecosystems are intricate networks of relationships, plants, herbivores, predators, decomposers, all depending on one another. When most of those relationships collapse, the system must slowly assemble itself again from the few species that remain. For millions of years following the extinction, life moved cautiously forward. Plants diversified into new forms suited to the altered climates. Small animals adapted to shifting landscapes where familiar habitats no longer existed. Food chains reassembled piece by piece. Insects played an important role in this recovery. Although the giant species had vanished, insects as a group proved remarkably adaptable. Their short life cycles and flexible diets allowed them to spread quickly through the recovering ecosystems. They pollinated plants, recycled organic material, and formed the base of new food webs developing across the land. But something fundamental had changed. The world that had once supported enormous arthropods no longer existed. The humid swamp forests of the Carboniferous had disappeared. Atmospheric oxygen levels had stabilized far below the peaks that once allowed insects to grow to extraordinary sizes. The conditions that created giant dragonflies and massive segmented arthropods would never fully return. Insects survived, but they survived in smaller forms. Their future lay not in becoming giants again, but in diversifying into countless species adapted to different environments. As the recovering ecosystems slowly grew more complex, Another group of animals began expanding into the roles left empty by extinction. While insects continued rebuilding the foundations of life, vertebrates were quietly preparing to reshape the balance of the planet in ways the ancient arthropods never could. As the Earth slowly recovered from the greatest extinction it had ever experienced, life did not simply return to its previous form. The rebuilding of ecosystems opened space for new possibilities, and certain animals were uniquely prepared to take advantage of them. Among the most important of these survivors were reptiles. During the early Triassic period, reptiles began spreading across landscapes that had once belonged largely to arthropods and amphibians. The environment was still harsh in many regions, but reptiles carried several advantages that allowed them to adapt to the changing world. Their bodies were supported by internal skeletons that could grow larger and stronger, without the constraints faced by creatures protected by external shells. Muscles attached directly to bone allowed powerful and flexible movement across uneven terrain. Equally important was the way reptiles breathed. Unlike arthropods, which relied on passive diffusion of oxygen through small openings in their bodies, reptiles used lungs that actively drew air inward. Oxygen traveled through their bloodstream, reaching muscles and organs efficiently even when atmospheric oxygen levels were lower than they had been in the ancient Carboniferous world. This ability gave reptiles a level of endurance that many earlier animals lacked, but perhaps their greatest advantage lay within their eggs. Encased in protective shells, reptile eggs could develop safely away from standing water. This freed reptiles from the ancient dependence that amphibians had on ponds and wetlands for reproduction. As ecosystems recovered and climates slowly stabilized, reptiles began exploring environments far beyond the old swamp forests. They spread across floodplains where rivers shifted through broad valleys. They moved into semi-arid landscapes where plants were only beginning to return. Over time, reptiles adapted to forests, plains, and coastal regions alike. The diversity of reptilian life began expanding in ways that hinted at a very different future. Across the early Triassic world, small reptilian predators hunted insects among sparse vegetation. Their bodies were agile and alert, built for chasing prey across open ground rather than hiding beneath dense swamp canopies. These animals were still modest in size compared to the creatures that would evolve later. The age of dinosaurs had not yet fully arrived, but the foundations of that future were already forming. With every passing generation, reptiles continued adapting to the recovering ecosystems around them. Some species grew larger, others developed specialized hunting strategies or new ways of moving through the environment. Slowly, the balance of life on land was shifting. Meanwhile, insects remained an essential part of the recovering world. They filled nearly every ecological niche available to small animals. Their populations were vast, their diversity remarkable. Yet their evolutionary path had changed. Without the high oxygen levels that once allowed enormous bodies to thrive, insects no longer grew to the extraordinary sizes seen in the Carboniferous forests. Instead, evolution guided them towards specialization. Some developed camouflage that allowed them to disappear among leaves and bark. Others evolved delicate wings suited for navigating new plant communities. Many adapted to specific diets and habitats within the recovering ecosystems. Insects remained abundant, but they no longer dominated the land as giants. The age of enormous arthropods had ended, and in its place a new chapter of Earth's history was unfolding. For the first time, vertebrates were becoming the primary architects of life on land. Reptiles were spreading across continents, shaping food chains and ecosystems that would eventually give rise to dinosaurs, birds, and many other creatures that followed. The world that once belonged to insects was slowly becoming a world shaped by vertebrates. Yet the memory of the ancient giants remained hidden within the rocks. Their fossils whispered of a time when insects ruled the sky and forests, and that memory raises an intriguing question. If giant insects once existed, could such creatures ever return to the earth again? The fossils of the Carboniferous world leave behind a question that has fascinated scientists for generations. If insects once grew to such extraordinary sizes, why did they never do so again? The answer begins with the atmosphere. During the age of giant arthropods, oxygen levels in the air were far higher than they are today. Those unusually rich conditions allowed oxygen to travel efficiently through the tracheal breathing systems inside insect bodies. Large wings, powerful muscles, and enormous bodies could function because oxygen could diffuse deep into tissues without difficulty. But after the great extinction at the end of the Permian period, that atmospheric balance changed. Oxygen levels slowly stabilized at concentrations closer to those we experience today. The modern atmosphere still provides enough oxygen for complex life, yet it no longer carries the extraordinary abundance that once filled the Carboniferous skies. For most animals, this difference is not especially limiting. Vertebrates breathe through lungs that actively pull air into the body. Their circulatory systems transport oxygen through blood vessels, delivering it efficiently to muscles and organs. But insects operate under a very different design. Their bodies rely on networks of narrow tubes that allow oxygen to move through passive diffusion. Air enters small openings along the exoskeleton and spreads through branching channels toward internal tissues. This system works remarkably well for smaller creatures, but as body size increases, the distance oxygen must travel through these tubes becomes greater. Eventually, the system can no longer supply enough oxygen to support larger tissues. Under modern atmospheric conditions, that limit appears much sooner. As a result, insects remain relatively small compared with many vertebrate animals. Yet the atmosphere alone does not explain everything. Another force quietly shaped the world that followed the extinction. Competition. In the millions of years after the Permian crisis, vertebrates began expanding into nearly every environment on land. Reptiles diversified into countless forms, eventually giving rise to dinosaurs that dominated ecosystems for millions of years. Later still, birds appeared. Vertebrates that had mastered flight in ways far beyond what insects could achieve. Birds filled the skies with powerful wings, sharp vision, and efficient lungs capable of sustaining long journeys through the air. And when mammals later evolved the ability to fly, bats joined them as agile hunters of the night. Together, birds and bats became dominant aerial predators across much of the planet. In a world filled with fast-moving vertebrate flyers, giant insects would face challenges far greater than those experienced by their ancient ancestors. Large insects gliding through modern skies would become easy targets for birds. At night, bats using echolocation would hunt them with extraordinary precision. Even if oxygen levels rose again, these predators would create intense pressure on any insects attempting to evolve enormous size. The ecosystems of the modern world follow very different rules from those of the Carboniferous wetlands. The skies are no longer empty spaces waiting to be claimed. They are crowded arenas where vertebrates dominate. And so, the age of giant insects remained a unique chapter in Earth's history. The giants did not disappear simply because a catastrophe wiped them away. They vanished because the planet that replaced their world was fundamentally different. The atmosphere changed. Forests transformed. New animals rose to dominate environments that had once belonged to arthropods. The rules of life had shifted, and when those rules changed, the giants of the ancient sky had no path back, yet insects themselves did not vanish. In fact, they continued evolving in ways that would make them some of the most successful organisms on Earth. To understand that success, the story must now move closer to the present. Because although the giants are gone, insects still shape the living world in ways most people rarely notice. The giants of the ancient forests vanished hundreds of millions of years ago. Their enormous wings no longer cross the sky, and the forest floor no longer trembles beneath the slow movement of creatures like Arthropleura. The age when arthropods dominated the land with sheer size has long since passed. Yet insects themselves never disappeared. In fact, they went on to become some of the most successful organisms the planet has ever produced. In the modern world, their presence is everywhere, though it often goes unnoticed. Across a quiet meadow, bees move patiently between flowers, carrying tiny grains of pollen from one plant to another. Each small flight helps fertilize the next generation of plants that will feed countless animals. Beneath the soil of a nearby forest, ant colonies stretch through intricate networks of tunnels. Thousands of workers move continuously through the darkness, gathering food, tending larvae, and shaping the soil in ways that influence the entire ecosystem above them. Along the edge of a still lake, dragonflies glide over the surface of the water. Their wings shimmer briefly in the sunlight as they hunt smaller insects drifting through the air. Scenes like these unfold across every corner of the planet. From tropical rainforests to deserts, from mountain valleys to urban parks, insects inhabit nearly every environment where life can survive. Their diversity is astonishing. Scientists estimate that millions of insect species exist on Earth today. Many remain unnamed and undiscovered, hidden in forests, soils, and waters where human eyes rarely look. When compared to other forms of life, insects dominate by sheer variety. The number of insect species alone exceeds the total number of mammals, birds, reptiles, and amphibians combined. Yet their importance extends far beyond numbers. Insects perform some of the most essential tasks in the natural world. Pollinating insects such as bees, butterflies, and beetles carry pollen between flowers, allowing plants to reproduce. Without them, many forests and agricultural crops would struggle to survive. Other insects act as recyclers. Beetles, termites, and countless tiny decomposers break down fallen wood, dead plants, and animal remains. Through their work, nutrients return to the soil where new life can grow. Even the smallest insects play a role in the complex web of life. They feed birds, reptiles, amphibians, and small mammals. Entire food chains depend on their presence. Remove insects from an ecosystem, and the effects ripple outward through every level of the environment. For all their small size, insects help sustain the balance of life across the planet. In a quiet way, they still rule the Earth, not through towering bodies or enormous wings, but through numbers, adaptability, and ecological influence. Their success lies in their ability to thrive in nearly every environment. They reproduce quickly, adapt to new conditions, and fill countless roles within ecosystems. While vertebrates may dominate the landscapes that humans notice most easily, insects form the hidden foundation beneath those systems. The forests that cover continents depend on pollinators and decomposers. Agricultural fields rely on insects that maintain soil health and plant reproduction. Even the air we breathe is influenced by plant life supported through insect activity. Without insects, the living world would look entirely different. Yet, despite their importance, insects often fade into the background of human awareness. We notice them briefly, when they pass our path or land upon a flower. Then they vanish from attention as quickly as they appeared. But when viewed from the perspective of deep time, insects stand among the most enduring groups of animals in Earth's history. They survived the greatest extinction events. They adapted to changing climates and landscapes. They evolved into millions of species occupying nearly every corner of the planet. The giants may be gone, but insects themselves remain extraordinarily successful, and their story carries an intriguing question. Because once, under very different conditions, insects grew to sizes almost unimaginable today, which leads scientists to wonder something fascinating. What might happen if the planet ever created those conditions again? The fossils of giant dragonflies and enormous crawling arthropods often leave people with a simple but fascinating question. If insects once grew so large, could they ever do it again? To explore this idea, scientists have turned to an unusual method. Instead of traveling through time, they recreate small pieces of the ancient atmosphere inside laboratory chambers. Within these carefully controlled environments, researchers adjust the amount of oxygen in the air. The chambers allow insects to live and grow while breathing conditions that resemble the atmosphere of distant geological periods. In some experiments, the oxygen concentration is increased well above modern levels, approaching the richer atmosphere that once existed during the Carboniferous Age. The insects inside these chambers experience something their distant ancestors once knew well: air filled with more oxygen. Researchers then observe how these insects grow. The results are subtle, but revealing. In many cases, insects raised in oxygen-rich environments grow slightly larger than those raised in normal air. Their bodies develop more efficiently because oxygen can travel through their tracheal systems with greater ease. Muscles receive oxygen more quickly, allowing tissues to grow without the limitations normally imposed by diffusion. The effect does not instantly produce dragonflies the size of birds, but the pattern is clear. When oxygen levels rise, insects gain the ability to grow somewhat larger than they typically would under modern atmospheric conditions. These experiments offer important clues about the ancient past. They suggest that the extraordinary oxygen levels of the Carboniferous world played a critical role in allowing arthropods to reach such enormous sizes. The atmosphere itself was part of the biological environment that shaped those giants. Yet oxygen alone does not tell the whole story. The ancient world that produced giant insects was defined by several conditions working together. The atmosphere contained abundant oxygen, but the landscape also mattered. Vast swamp forests covered the continents, creating humid ecosystems where large arthropods could survive without drying out. Thick vegetation supported enormous populations of insects, providing abundant food for larger predators. Equally important was what did not exist. The skies of the Carboniferous world were empty of vertebrate flyers. Birds had not yet evolved, and bats would not appear for hundreds of millions of years. Giant dragonfly relatives could glide across the wetlands without facing powerful aerial predators. The modern world is very different. Today the skies are crowded. Birds fill the air during the day, scanning the ground and vegetation for insects. At night, bats sweep across fields and forests, using echolocation to hunt with remarkable accuracy. If giant insects were to appear today, they would quickly attract attention from predators that specialize in catching flying prey. Even if oxygen levels rose slightly above modern values, the conditions that once allowed enormous arthropods to flourish would still be missing. The ecosystems that shaped those creatures no longer exist. The vast Carboniferous wetlands are gone. The ancient balance between atmosphere, vegetation, and animal life has long since changed. The experiments conducted in laboratories offer a glimpse into what once was possible, but they also reveal something deeper. The giant insects of the past were not simply larger versions of modern species. They were products of a very specific moment in Earth's history, a time when the atmosphere, the forests, and the structure of ecosystems aligned in a way that allowed evolution to explore extraordinary possibilities. That moment passed long ago. The modern world follows different rules, yet the story of those ancient giants still offers valuable insight into how life responds to changing planetary condition. And as the narrative moves toward its final chapters, their story becomes part of a much larger reflection about evolution, deep time, and the ever-changing nature of the planet itself. The age of giant arthropods ended hundreds of millions of years ago, yet the memory of that world has never completely vanished. It remains preserved within stone. Across mountains, deserts, and river valleys, layers of ancient rock hold quiet records of environments that existed long before the first dinosaurs appeared, long before mammals evolved, long before humans walked the earth. In laboratories and museums around the world, scientists carefully examine these fragments of the distant past. Some of the most remarkable discoveries come from fossils that seem almost impossibly delicate. Thin slabs of stone sometimes reveal the faint outlines of ancient insect wings, each vein preserved in astonishing detail after hundreds of millions of years. When paleontologists uncover these fossils, they are not simply finding pieces of stone. They are uncovering moments from a vanished world. One famous example comes from the wings of Meganeura, the giant dragonfly relative that once glided above Carboniferous forests. Preserved impressions show wings stretching across lengths that rival those of modern birds. Each tiny structural detail remains visible, offering clues about how these insects flew through the humid air of their ancient environment. Other fossils reveal the presence of creatures that moved across the forest floor. Long trails etched into prehistoric sediments record the slow passage of enormous arthropods. These fossilized trackways show how massive segmented bodies once crossed muddy wetlands that have long since hardened into rock. Occasionally, fragments of ancient exoskeletons appear as well. These pieces of armor, once part of giant arthropods, provide scientists with evidence about body structure, movement, and evolutionary relationships among early insects and their relatives. Taken together, these discoveries allow researchers to reconstruct entire ecosystems that vanished hundreds of millions of years ago. Through careful study, scientists can imagine the towering forests, that once covered equatorial regions. They can trace the relationships between plants, insects, and predators that shape those ancient environments. What emerges from this research is a reminder that the giant insects were not isolated curiosities. They were part of a fully functioning world. The Carboniferous ecosystems operated under conditions very different from those of the modern planet. The atmosphere held more oxygen. Vast wetlands covered continents. Evolution explored possibilities that would never appear again. The age of giant arthropods was one of many evolutionary experiments shaped by those conditions. Throughout Earth's history, life has never followed a single predictable path. Instead, it has adapted continuously to changing environments. Different climates, different atmospheric conditions, and different landscapes create entirely new possibilities for evolution. At certain moments in deep time, those possibilities produce creatures that seem almost unbelievable when viewed from the perspective of the modern world. For a brief chapter in the planet's history, insects became giants. Dragonflies the size of birds ruled the skies. Massive arthropods crawled across forests that no longer exist. The balance of life followed rules very different from those we know today. Then the planet changed. The forests vanished. Oxygen levels declined. New animals rose to dominate the land. Evolution moved in another direction. Yet the evidence of that earlier world remains hidden within layers of ancient rock. Each fossil discovered today serves as a quiet reminder of the extraordinary diversity life has achieved throughout Earth's history. The rocks remember a time when the skies belonged to creatures that no longer exist. And by studying those ancient worlds, scientists gain more than knowledge of the past. They gain insight into how life responds when the planet itself begins to change. In the quiet halls of natural history museums, time seems to move differently. Glass cases line the walls, each holding fragments of ancient worlds. At first glance they appear simple stones, impressions, pieces of hardened sediment. But to the scientists who study them, these objects carry stories older than mountains. A slab of rock may contain the faint outline of an insect wing. Another might preserve the delicate segments of a creature that once crawled across a prehistoric forest floor. Nearby, a long trail etched through ancient mud reveals the slow passage of something enormous that moved across the earth hundreds of millions of years ago. These fossils are not simply relics of strange creatures that vanished long ago. They are pieces of a much larger record. In laboratories around the world, paleontologists study these remains with careful attention. Each fossil offers clues about the environment that produced it. The shape of a wing, the thickness of an exoskeleton, even the pattern of a creature's footsteps can reveal details about the conditions under which it lived. The rocks themselves become a kind of memory. Layer by layer, they preserve the history of life on Earth. Some layers record flourishing ecosystems filled with diversity. Others reveal sudden disappearances, moments when entire groups of organisms vanish from the record almost overnight. By studying these patterns, scientists learn how life responds when the planet changes. The age of giant arthropods is one of the most fascinating examples hidden within this geological memory. When researchers examine fossils of enormous dragonfly relatives like Meganeura, they see more than an insect with unusually large wings. They see evidence of a world with an atmosphere very different from our own. Those wings could only function in air rich with oxygen. Similarly, the trackways left by massive arthropods such as Arthropleura reveal ecosystems that supported creatures far larger than modern insects. Their size suggests humid landscapes filled with vegetation and stable environmental conditions that allowed arthropods to grow to extraordinary scales. Each fossil is a clue. Taken together, they allow scientists to reconstruct entire environments that disappeared hundreds of millions of years ago. Through these discoveries, the ancient Carboniferous world begins to take shape again. Researchers imagine vast wetlands stretching across equatorial continents. Towering plants fill the humid air, and enormous insects glide through skies empty of birds. The forest floor is alive with giant arthropods moving slowly through thick vegetation. It was a world built on very different rules, and yet the fossil record also reveals how temporary that world was. In higher rock layers, the giants begin to disappear. Their fossils grow rarer, replaced by evidence of smaller insects and expanding reptile populations. Eventually, the enormous arthropods vanish entirely from the record. The rocks quietly document the end of their age. This pattern appears again and again throughout Earth's history. The fossil record shows that life does not move in a straight line toward a final destination. Instead, evolution unfolds through a series of experiments shaped by changing environments. When conditions shift, life adapts in new directions. Some organisms flourish under those conditions, yet others disappear when the world no longer supports them. The age of giant insects represents one of these remarkable experiments. For a brief chapter in geological time, the atmosphere, climate, and ecosystems aligned in a way that allowed arthropods to become the dominant giants of the land and sky. Then the planet changed, and evolution moved forward once again. Every fossil discovered today carries a message from those vanished worlds. Each one tells us something about the environments that once existed and the forces that shaped the living planet. And when scientists read those messages carefully, they begin to see a deeper truth hidden within the rocks. If the Earth once created such strange and extraordinary worlds before, the question naturally follows, could the planet ever do it again? The discovery of giant insects in the fossil record naturally leads to a fascinating question. If the Earth once created conditions that allowed insects to grow to such extraordinary sizes, could those conditions ever appear again? At first, the idea may seem unlikely. The modern world feels stable and familiar, governed by atmospheric conditions that rarely change within a human lifetime. The air we breathe contains about 21% oxygen, a balance that has supported ecosystems for thousands of years. Yet, when scientists examine the deeper history of the planet, they discover that this balance has never remained constant. Over hundreds of millions of years, the chemistry of the atmosphere has shifted repeatedly. During the Carboniferous Period, oxygen levels rose far above modern concentrations. Later, during other chapters of Earth's history, oxygen declined again as volcanic activity, climate changes, and shifting ecosystems altered the balance of gases in the air. The atmosphere is not fixed, it is shaped continuously by life itself. Forests release oxygen through photosynthesis. Oceans absorb and release gases depending on temperature and biological activity. Volcanic eruptions introduce new gases into the atmosphere, while microscopic organisms in soil and water quietly regulate chemical cycles across the planet. Together, these forces create a dynamic system. The balance of oxygen, carbon dioxide, and other gases changes slowly over immense spans of time. Because of this, scientists know that the atmosphere of the distant future may not look exactly like the one we experience today. In theory, if environmental conditions change dramatically enough, oxygen levels could rise again. Expanding forests, shifts in ocean chemistry, or large-scale geological processes could alter the atmospheric balance in ways similar to those seen in ancient eras. Such changes would not happen quickly. They would unfold across millions of years, far beyond the timescale of human history. But the possibility exists. If oxygen levels were to increase significantly, insects might once again experience fewer biological limits on their size. Their tracheal breathing systems would become more efficient in oxygen-rich air, allowing their bodies to support greater mass than they can under modern conditions. Yet the atmosphere is only part of the story. The world that produced giant insects contained several conditions that worked together in unusual harmony. The Carboniferous wetlands were vast and humid, providing ideal environments for large arthropods. Dense vegetation supplied abundant food and shelter. Perhaps most importantly, the skies remained largely empty of vertebrate predators. The modern world is very different. Today, birds dominate the daytime skies across most ecosystems on Earth. Their sharp vision and powerful wings make them highly effective hunters of insects. At night, bats patrol the air with remarkable precision, detecting flying prey through echolocation. Their hunting abilities allow them to capture insects even in complete darkness. These predators occupy ecological roles that did not exist during the age of giant arthropods. If enormous insects attempted to evolve again, they would face intense pressure from creatures that specialize in hunting airborne prey. Competition would also come from other vertebrates that now dominate many terrestrial ecosystems. Even if oxygen levels rose again, the ecological landscape has changed dramatically since the Carboniferous age. The world that allowed giant insects to thrive was built on a rare combination of atmospheric chemistry, climate, vegetation, and ecological opportunity. Recreating all of those conditions together would require the planet to return to a very specific state. And while Earth has changed many times before, it may never again assemble the same combination of factors that once allowed insects to rule the sky as giants. The planet could certainly change again. Atmospheres evolve, ecosystems shift, new environments emerge over geological time. But the ancient world that produced dragonflies the size of birds and arthropods longer than a human arm may remain one of the most unique chapters in Earth's history. And that realization invites a deeper reflection about the nature of life on this ever-changing planet. The story of giant arthropods might seem, at first, like an unusual footnote in the history of life, a brief and curious chapter when insects grew to astonishing sizes before disappearing from the world they once dominated. But when scientists step back and examine the broader history of the planet, the age of giant insects begins to look less like an anomaly and more like part of a repeating pattern. Life on Earth has never followed a straight path. Instead, it unfolds through cycles, moments of innovation, expansion, collapse, and renewal. Across hundreds of millions of years, entirely different groups of organisms have taken turns shaping the living world. In the earliest ages of complex life, the oceans belonged primarily to marine invertebrates. Trilobites crawled across ancient sea floors while strange soft-bodied creatures drifted through prehistoric waters. For immense spans of time, these organisms dominated marine ecosystems. Then the balance shifted. New predators appeared. Fish evolved powerful jaws and streamlined bodies capable of hunting in ways earlier creatures could not. The ocean slowly transformed as vertebrates began occupying roles that invertebrates once held. Later still, life expanded onto land. Plants spread across continents, creating the first terrestrial ecosystems. Arthropods followed, exploring forests and wetlands, long before vertebrates became common on land. For a remarkable stretch of geological time, the land belonged largely to arthropods. The Carboniferous forests became the stage for some of the most extraordinary creatures evolution had ever produced. Giant dragonfly relatives ruled the skies. Massive segmented arthropods moved across forest floors that stretched for thousands of kilometers. To any creature living within that world, the dominance of arthropods must have seemed permanent. The forests were vast. The atmosphere supported enormous bodies. The ecosystems appeared stable. Yet the planet was already changing. The rise of reptiles, the shifting of continents, and the transformation of atmospheric chemistry gradually reshaped the environment. Eventually, the age of giant arthropods ended, replaced by a world where vertebrates took the leading role. The pattern continued. During the Mesozoic era, reptiles, especially dinosaurs, dominated the land for more than 150 million years. Their enormous bodies and diverse adaptations made them the most powerful animals on Earth. But even their long reign eventually came to an end. A massive asteroid impact and the environmental upheaval that followed reshaped ecosystems once again. Dinosaurs vanished and mammals, small and largely unnoticed during the age of reptiles, expanded into the ecological roles left behind. Today mammals and birds shape much of the modern world. Cities, farms and forests reflect ecosystems where vertebrates occupy many of the dominant positions. Yet the deeper lesson of Earth's history remains clear. No single group rules the planet forever. Every era that seems stable eventually gives way to change. Environments shift, climates transform, and evolution continues exploring new possibilities. The age of giant insects is one example among many. For a brief moment in geological time, the conditions of the Earth aligned in a way that allowed arthropods to grow to extraordinary sizes. Their bodies and ecosystems matched the environment perfectly. Then the environment changed. The forests vanished. Oxygen levels declined. New competitors emerged. The giants faded from the world they once dominated, and evolution continued forward, shaping entirely new landscapes of life. The rulers of Earth have changed many times. Each dominant group thrived under the conditions of its own era, and in every case, those conditions eventually shifted, which leaves us with a quiet and intriguing thought. The world we know today may feel stable and permanent, but in the long story of the planet, it is only one chapter among many. And the forces that shape the rise and fall of ancient giants are still at work, quietly shaping the future of life on Earth. In the present day, the Earth appears calm and familiar. Forests stretch across hillsides where sunlight filters through leaves, and birds fill the air with quiet songs. Meadows sway gently in the wind, while bees drift from flower to flower, carrying pollen between bright blossoms. Rivers move steadily through valleys, reflecting the sky as fish glide beneath their surfaces. To the human eye, these scenes feel permanent. We walk through parks and forests believing that the living world around us has always looked this way. Birds circling above, insects humming softly in the grass, mammals moving cautiously through the undergrowth. All of it seems like the natural order of things. It is easy to assume that the ecosystems we know today represent a stable balance that has existed for ages. Yet the deeper story of the planet tells something very different. Every element of the modern world exists because of countless changes that unfolded across billions of years. The air we breathe, the plants that grow across continents, and the animals that move through forests and oceans are all the result of a long chain of environmental transformations. If even one of those changes had occurred differently, the world we know might look completely unfamiliar. The absence of giant insects, for example, feels entirely normal to us. A dragonfly passing quietly above a pond seems small and delicate. A millipede moving slowly across the soil appears harmless and modest in size. We rarely imagine these creatures as anything more than minor details in the living landscape, but for a vast span of Earth's history, insects were anything but small. During the Carboniferous Period, dragonfly relatives soared through the skies with wings that stretched wider than a human hand. Massive arthropods crawled through dense swamp forests, their bodies longer than many modern animals. To the creatures living in those ancient ecosystems, such giants were ordinary. The skies filled with enormous insects would have felt as natural to them as birds do to us today. The slow movement of giant arthropods across the forest floor would have been as familiar as the rustle of leaves in a modern woodland. What feels unusual to us now would have seemed perfectly normal in that distant world. And the creatures living there would have had no reason to imagine that their environment might one day disappear. Yet the planet changed. Forests vanished, oxygen levels declined, and entirely new animals rose to dominate the land. The ecosystems that supported giant insects slowly faded into history. The modern world replaced them. Birds now fill the skies that once belonged to giant dragonflies. Mammals roam landscapes that once supported enormous arthropods. The balance of life has shifted so completely that the earlier world feels almost impossible to imagine. But it was real, and for millions of years it was simply the way the planet worked. This realization invites us to see the modern world in a new light. The ecosystems surrounding us are not permanent structures that will exist forever. They are temporary arrangements shaped by the current conditions of the Earth, its climate, its atmosphere, and the complex relationships between living organisms. Those conditions have changed many times in the past, and when they change, life responds. New species appear, others disappear. Entire ecosystems transform into forms that would once have seemed unimaginable. The forest we know today may someday evolve into something entirely different. The animals that dominate the land now may one day be replaced by others better suited to future environments. The world we see today feels permanent, but in the immense timeline of the planet, it is only one chapter in a story that has been unfolding for billions of years. And understanding that truth leads to a deeper realization about life itself. The story of giant insects ultimately reveals something larger than the creatures themselves. It reveals the restless nature of the planet they lived on. From the perspective of human life, the Earth appears steady, mountains rise in familiar places, oceans remain within their shorelines, and the continents seem fixed beneath our feet. Generations pass with little visible change in the shape of the world. Yet beneath this calm surface, the planet is constantly in motion. The ground we walk on is part of enormous tectonic plates slowly drifting across the Earth's mantle. Over millions of years, these plates collide, separate, and slide past one another. Entire oceans open and close. Continents gather into supercontinents and later break apart again. The world that existed 300 million years ago looked nothing like the map we recognize today. The Carboniferous forests where giant arthropods once lived were shaped by continents, arranged in entirely different positions across the globe. But geological motion is only one part of the story. Deep within the Earth, volcanic forces continue releasing gases that influence the chemistry of the atmosphere. Over vast spans of time, these gases interact with oceans, forests, and microscopic life forms to shape the balance of oxygen and carbon dioxide in the air. Even the smallest organisms play a role in this planetary system. Algae drifting through oceans produce oxygen through photosynthesis. Microbes in soils recycle nutrients and influence the chemistry of the land. Forests spread across continents, absorbing carbon dioxide and releasing oxygen into the atmosphere. Together, these forces create a complex system that is always adjusting. When one part of the system changes, others respond. The age of giant arthropods emerged from one such chain of changes. Vast forests altered the atmosphere by producing enormous amounts of oxygen. Humid wetlands created environments where arthropods could thrive. The absence of aerial vertebrates allowed insects to dominate the skies for a remarkable period of geological time. Those conditions aligned perfectly. The result was a world filled with insects larger than anything alive today. But the same forces that created that world eventually reshaped it. Continents drifted together, altering climate patterns. Wetlands shrank as environments grew drier. Oxygen levels gradually declined as ecosystems shifted. As the conditions that supported giant insects faded, the giants themselves disappeared. Evolution did not stop when that happened. Instead, life adapted to the new environment. Reptiles expanded into the ecosystems left behind. Later, birds and mammals evolved, filling the skies and landscapes with new forms of life. Each era produced its own dominant creatures, shaped by the conditions of the planet at that moment. And through all of these changes, the Earth continued evolving. The same forces that once raised oxygen levels in the Carboniferous atmosphere still operate today. Forests still influence the chemistry of the air, oceans still regulate global temperatures, volcanoes still release gases from deep within the planet. The world is never truly still. Every ecosystem, every atmosphere, every landscape represents only a temporary balance between geological and biological forces. The age of giant insects reminds us of this truth. It shows how dramatically life can change when the planet itself shifts. And it reminds us that the same forces that shaped ancient worlds continue shaping the future of life on Earth. The story of evolution is not finished. It is still unfolding quietly all around us. Imagine the planet as it once was. The air is warm and heavy with moisture. A hazy orange light filters through towering forests that stretch endlessly across the horizon. The ground is soft beneath thick layers of fallen vegetation, and shallow pools of dark water reflect a sky unlike the one we know today. This is the Carboniferous world. 300 million years ago, these wetlands covered vast regions of the Earth. Forests of strange plants rose from the waterlogged soil, their trunks patterned with scales and ridges, unfamiliar to modern eyes. Dense vegetation filled the humid air, creating an environment where life flourished in forms rarely imagined today. Above the forest canopy, something moves through the mist. A shape glides slowly across the sky. At first glance, it resembles a dragonfly, but as it passes closer, its size becomes unmistakable. Wings stretch wide across the air, longer than a human arm. The creature drifts silently above the treetops before disappearing again into the haze. Below, the forest floor is alive with quiet motion. Massive segmented bodies move slowly through the thick vegetation. Giant arthropods crawl across fallen branches and damp soil, their armored plates glinting faintly in the filtered sunlight. For millions of years, this world existed exactly as it appears here. The creatures that lived within it were perfectly adapted to its conditions. Oxygen-rich air filled their breathing systems. Endless wetlands provided shelter and food. Ecosystems formed intricate networks where every organism played its role. To the animals that lived there, the world must have seemed stable and permanent. The forests stretched across continents. The skies belonged to giant insects. The balance of life appeared unchanging. Yet beneath the quiet surface of that ancient world, the planet itself was already moving. Continents drifted slowly toward one another. Climate patterns shifted. The chemistry of the atmosphere began to change in ways no creature could perceive. Over millions of years, the conditions that supported this extraordinary ecosystem slowly faded. The wetlands shrank. Oxygen levels declined. New animals evolved that would thrive under the changing rules of the planet. And gradually, the giants disappeared. The dragonflies with wings like birds vanished from the skies. The massive arthropods that once moved across forest floors faded from the fossil record. The world that created them transformed into something entirely different. Today their presence remains only in stone. Hidden beneath layers of ancient rock, the fossils of those creatures preserve the memory of their time. Impressions of wings, fragments of exoskeletons, and trails left in prehistoric mud tell the story of a world long gone. Scientists uncover these clues piece by piece, reconstructing the ecosystems that once shaped the living planet. Each discovery reminds us how extraordinary Earth's history truly is. The world we know today is only the latest chapter in a much longer story. Before the rise of mammals, before the age of dinosaurs, before even the first birds filled the air, the skies of Earth belonged to creatures that no longer exist. The age of giant insects was one of many strange worlds the planet has hosted. And somewhere beneath our feet, preserved quietly in the rock, the memory of those giants still remains, waiting for us to remember that the history of life on Earth is far stranger and far more dynamic than the world we see today.